Good morning to all of you. I hope you all are doing great. So let's get started. Today we'll be talking about polysaccharides. So what are polysaccharides? Have a look. Polysaccharides on hydrolysis, that is acid hydrolysis, can give more than 10, correct, monosaccharide units. So when you do the acid hydrolysis of polysaccharides, you are supposed to get more than 10 monosaccharide units. I hope everybody among you has understood this thing. Let's take few examples which we are discussing in this particular topic. Our main example will be starch, glycogen and cellulose. These will be our three polysaccharides which we will be discussing here today. My dear friends, let's talk about the starch first. Have a look. Starch is our polysaccharide. You should know that. I've already told you. It is main storage polysaccharide in plants. When green plants prepare their food, like through a process called as photosynthesis, and then that glucose production in case of plants is stored in the form of a polysaccharide called as starch. When green plants produce glucose, those glucose molecules are polymerized, means they are converted into the polysaccharide. Which polysaccharide? Starch. So starch is actually the food content being present in plants. Okay. Second point, it is the most common dietary source of human beings. Especially we human beings will take on, cereals, roots, tubers and vegetables. So in our diet we need starch. When you take rice, when you take cereals, when you take tubers, roots, so obviously all these substances do contain starch. So it's a main component of our diet as well. We need starch. From starch we obtain glucose, and that glucose is an important source of energy for all of us. And let us talk about now this starch. Starch is a polymer. Polymer means basically here which is made up of more than 10 monosaccharides here. Okay. So this polymer we talk of, it's a starch polymer. It is made up of alpha D glucose molecules. So our polymer starch is made up of alpha D glucose molecules. So it's a polymer of alpha D glucose molecule. I hope you have understood, my dear friends. Please make note of this particular thing. And after this, we will have a discussion about the starch contains two components actually, amylose and amylopectin, that we'll discuss after this. Please make note of this. Look here about the starch. Starch consists of two components. So our starch contains two components. The first component is amylose. Have a look here. Please focus here. It is water soluble. Amylose is one of the component of starch, and this is water soluble. Another component of starch is amylopectin. It is insoluble in water. That means our starch has two components in it. One is amylose and one is amylopectin. Amylose part of starch is soluble in water, but amylopectin part of starch is insoluble in water. Correct? So let's look at the second point. Please focus here. This amylose, which is a component of starch, it is water soluble and it makes 15 to 20% of starch. So 15 to 20% of starch is made of amylose, and that is soluble in water. Now look here, folks here. This amylopectin makes 80 to 85% of starch. But this 80 to 85% of starch is insoluble in water. Correct? Let's have a look at the third point. If we talk of this amylose is a linear polymer. Linear polymer means its chain will be like this. The glucose units will be linked in this form. So it's a linear polymer. These are glucose molecules. Which glucose molecule you can take? Alpha D plus glucose you can take. Let's suppose this is alpha D glucose, and the chain is linear. You can also draw it like this. We have a linear chain here. So this is linear polymer. Consider these as sugar molecules like alpha D glucose. So it's a linear polymer. Have a look. And in this linear polymer, it contains how many alpha D glucose molecules? 200 to 1000 alpha D plus glucose molecules. Let us suppose these are alpha D glucose molecules. And how many are there? 200 to 1000 alpha D glucose molecules are present in amylose. And amylose is one of the components of starch. And you know one thing? Glycosidic bond is present between monosaccharides. Obviously, between alpha D glucose units there will be a glycosidic bond. But that glycosidic bond will be between carbon number 1 of one sugar with the carbon number 4 of another sugar. That means the glycosidic bond will be here COC bond type, glycosidic bond. So it will be between carbon number 1 of this sugar with carbon number 4 of this sugar. Then carbon number 1, carbon number 4, carbon number 1, carbon number 4, carbon number 1, carbon number 4, like that. It goes on. So my dear friends, in case of amylose, we will have 200 to 1000 alpha D glucose molecules in it. And these molecules are arranged in a linear chain. So it's a linear polymer. Amylose is a linear polymer because 200 to 1000 alpha D glucose molecules are arranged in a straight chain. And between glucose molecules we know there exists a glycosidic bond. And that glycosidic bond is between carbon number 1 of one sugar with the 4th carbon of another sugar. Carbon first of first sugar with the carbon 4 of next sugar. So such glycosidic bonds will be there in amylose. And it's a linear polymer. Correct? But when we look at amylopectin, it's insoluble in water, makes 80 to 85% of starch. Now look here, it's a branched polymer. That's important. It's a branched polymer. When it's a branched polymer, you cannot directly draw the branch. No. For branching also, first of all, you need a linear chain. For branching also, you need a linear chain. So, it's a branched polymer, but for branching, you need a linear chain, and then on that linear chain, you can draw the branch, or you can make the branch on that. This is the branch on that linear chain. Now, two types of bonds are found here. Two types of glycosidic bonds. First of all, when I draw the linear chain for the branched polymer, what is that? Amylopectin. For example, if I have a linear polymer first, then only I can do the branching. Branching is possible. Or if I have a linear polymer, then only branching is possible. So this guy will have two parts. First of all, we will have, it's a branched polymer. First of all, we will have a chain here. And that chain will be basically a linear chain actually. And that is formed between C1 and C4 carbon atoms. And that will be the glycosidic bond. That means here it will be between C1 versus C4. So C1, C4. Now I told you it's a branched polymer. What is the meaning of branched polymer? You need a chain first. After that, you have to draw the branching. Once you start branching, the branching will be between C1 and C6. That is, let us suppose we have a C1 of any glucose molecule. It will be branched with the 6th carbon of another glucose molecule. Let us suppose in this case we have a C1 carbon here, and it's branched with the another glucose unit. and here let us suppose we have a carbon number 6. So it should be branched with the C6. So C1 and C6 linkage is here. So it will form a branch. So this is branch here. So first of all I have to draw a linear chain. On that linear chain I have to do branching. Correct? Linear chain is due to glycosidic bond between C1 and C4. Okay? And the branching happens between C1 and C6. So in case of amylopectin you have two types of bonds. One is C1-C4 bonding and another one is C1-C6 bonding. So let us understand it in detail. So my dear friends, let us understand first of all amylose, structure of amylose. I told you that it's composed of alpha-D glucose molecules. So let me draw the structure of alpha-D glucose here. So this will be your alpha form. Please have a look. H, OH, OH, H, H, OH, H and CH2OH. So this is first carbon, second carbon, third, fourth, fifth and sixth. So let me draw one more molecule here. At least 2-3 molecules I will draw to show you the exact what is happening. Cool. What happens here? H, OH, and here we have H and OH. OH, H, H, OH, finally OH, H, H and CH2OH. Now let's go here, H, OH, OH, H, H, OH, H and then you have CH2OH here. Now my dear friends, this is alpha D glucose. This is again alpha D glucose. This is again alpha D glucose. When we talk of amylose, I told you that there is a bond. Which bond linkage is there? There is basically a bond linkage called as alpha 1,4 glycosidic bond. Should be there. So now let's understand this. And we also told one more thing. It is a linear polymer. So amylose is a linear polymer. Correct? So let's understand. I have taken alpha D glucose, alpha D glucose, alpha D glucose. So we will be having thousands of these molecules, but I can't draw all the 1,000 molecules here. So let me show you. It's an interaction between first carbon with fourth carbon. Correct? This is the carbon number 1 of one sugar and this is the carbon number 4. C1-C4 bond is there. C1 and this is C4. 1, 2, 3, 4. So C1-C4 linkage. What will be lost here? Have a look, please have a look. What will be lost here? Water. So OH and H will be lost here. Now C1 is here and now C4 is here. 3, 2, 1. Okay, my dear friends, what will be lost here again? Water will be lost here. So at two places you are making it to lose water. So now, my dear friends, if water is lost here, okay, please have a look first of all. I can't write separately, I want to write here only. So I will remove OH from here and I will remove H from here. So what is lost here? Minus H2O, what is lost? So which bond is formed? Oxygen is here now. So it is C1, carbon number 1 and this is carbon number 4. So there will be a COC bond. Now let us represent that COC bond here. COC bond is formed here with the loss of water. Same thing will happen here. H2O will be lost. What will remain here? Oxygen will remain here. So this is C1 and this is C4. So what is the possibility between C1 and C4? A bond will be formed, COC bond. So let me draw here. COC bond is formed. And here also water molecule is lost. Correct? Now alpha D glucose molecule, alpha D glucose molecule, alpha D glucose molecule. How many times they can combine to form a linear polymer? Linear polymer of what? We need a linear polymer of amylose. How many times they should combine? Thousands of times, because I mentioned it. So these molecules have to be thousands of times. So but I can't draw it thousands of times. So what I am doing actually, if I draw one more structure here, let's suppose, that will give, this will give H and that will give OH. Then what will be here? Formation. What will be the formation here? Again here, COC bond will be formed with this molecule, let's suppose. Correct? So let me draw it now like this. Let me show it like this now. There will be this is C1, then this will be attached with the C4, carbon number 4 of another sugar. But I can't show it this much. So what I'm going to do, I will only represent C1O. What should be here now? C4 like this. We should have here fourth carbon like this. But I will not mention this sugar because it will become lengthier. So I will write down it how many times? N times, my dear friends. So I am writing it N times. Now, on this particular side, okay, the chain is not growing on this side. You may think that this is carbon number 4. It will react with carbon number 1. Then carbon number 4 will react with carbon number 1. So this side also chain will grow. No. This side, at this particular point, okay, initiation will happen. Okay. And usually when we talk of organic chemistry, we are using basically certain initiators like benzoyl peroxides we are using in organic chemistry for initiation of reaction. Actually this part will be also occupied. Which thing is here now? I can also represent it in this way like this. So this part is basically blocked. Okay? Or we can say that right from here the initiation happens. Or this is the part where the initiation of the polymer formation happens. So it will keep on growing and all. So I will write down on this side that it will grow N times. Here the chain will be capped. We call it as a capping. You will understand it in biology. Capping is happening right out here. And here the chain will grow N times. So you can add thousands of molecules of alpha D glucose here. And now you know this bond is your what? Alpha 1,4 glycosidic bond. And this bond is your what? Alpha 1,4 glycosidic bond linkage. And now this molecule, after the combination of these alpha D glucose molecules, how many times, my dear friends? How many times? N times. Okay? There is a bond formation now between them. Which bond is formed between them? Can you tell me? Glycosidic bond is formed between them. You can represent it like this also. Here you can mention oxygen. And here the chain is basically capped or initiation of reaction takes place here. So what happens here? Now we are getting a molecule called as amylose. So this is our amylose structure and it is a basically linear polymer. I hope everybody among you has understood the structure of amylose. After this we'll be talking about amylopectin. In amylose we have C1-C4 linkage, C1-C4 linkage, and those are basically the glycosidic bonds, alpha 1,4 glycosidic bonds. How many times these molecules are interacting? They are interacting N times, thousands of times they are interacting to make amylose structure. So my dear friends, let us talk about now amylopectin, what this amylopectin is all about. When we look at the structure of amylopectin, okay, we have to take in consideration 2 points. The first point is that it is a branched polymer. It's a branched polymer. Second thing, linkages are 2 types here. We will have here alpha 1,4 glycosidic linkage bonds here, and we will be also having here alpha 1,6 glycosidic bonds. So 2 types of glycosidic bonds are here, okay, in amylopectin. So this will make a chain. This does form a chain. Which chain it will form? It will form a linear chain actually. And this will make this is for branching. So this alpha 1,4 glycosidic bonds are for chain making, okay? You can also call that it makes a linear chain. For example, if you have a plant It has to be beginning, it has to be a linear. Let's suppose these are the roots of a plant. It has to be linear at the beginning. Then only branching will start. When you have basically a linear stalk here, on that linear stalk you can have branches. Okay? In the same way, for amylopectin, you need to have a chain. Which chain you need to have? You need to have a linear chain first. It makes a linear chain first. Then on that linear chain, you will be having branching. Linear chain is formed in amylopectin through 1,4-glycosidic bond. And finally, branching is also happening through 1,6-glycosidic bonds. Have a look. Let's suppose this is the linear chain formation. Linear chain formation. Which molecule you are taking? Absolutely you are taking alpha D glucose. You are taking alpha D glucose. Cool. And which kind of glycosidic bond you will form? COC. Correct? So directly I am showing the bond formation, COC. Here also you can make one more COC bond. Okay. Let's suppose you are making one more COC bond here. Is it clear, my dear friends? So, in this particular case, let's suppose chain can grow n times here. Then it will become, let's suppose if I write it like this, and I will take one oxygen here. Here I am doing the capping process. Then it will become your amylose. It will become your amylose. But if I do the branching on this, it becomes amylopectin. So let us understand how can I do the branching on this particular thing. Let me remove it for time being. Okay. Let me make it available here as OH. Correct. Here we will be having H and here also H. Now my dear friends, H, OH, OH, H. Here you have H, H and CH2OH. H, CH2OH. And here again we have H, CH2OH. So this is your alpha D glucose molecule. They are linked through which bonds now? COC bond. COC bonds, they are linked. Okay, cool guys. In this way I will represent it like this. Capping is done here. But on this side, if you find out carbon number 1, carbon 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6 we have. Here 1, 2, 3, 4, 5 and 6 we have. So my dear friends, let us understand how the branching takes place. All are alpha D glucose molecules. Let's understand. Branching will be between, look here, alpha 1,4-glycosidic bonds will make linear chain. If you look at this linear chain, okay, it looks like amylose. But I have to draw amylopectin. So what is happening? Branching should happen. Branching should happen. So what will happen? Branching will happen between carbon number 1 and carbon number 6. Branching is happening. Have a look. This is my carbon number 1 here. And let me draw one structure here. Please focus here. Clear? So after that, let's have a look. This is the carbon number 6 here. CH2. Okay. I can draw it on this side as well. OH. H. Then you have H. OH. H. OH. OH. H. Finally OH. H you have. Now look here. This is carbon number 1. And this is carbon number 6. So 1, 2, 3, 4, 5 and 6. So there is a bonding between carbon number 1 and carbon number 6. So what will be removed from here? H2O will be removed from here. Water. There is a loss of water. When water is lost here, H2O is lost here. You can see now how will be the bond formation now after the loss of water. So it will be like this. So there is a bond formation now after the loss of H2O. Now it is between first carbon and sixth carbon. So it is a branching only. Okay, so branching has happened between first and sixth carbon. Glycosidic bond is formed. Through that bond formation, there is a branching has happened. Now you can continue with this in this way here. Okay, between first carbon and fourth carbon, you can continue like this. Okay, let's have a look. So you can put it how many times? N times H, OH. Here you have H, OH, H. This is fourth carbon, H, CH2, OH. And then you can continue from here as well, between fourth and first carbon. Correct? So here you'll be having first, second, third, fourth, fifth, and sixth carbon. So there will be again COC bond here. So my dear friends, then finally at this point, I can mention it like O, and there will be a capping. It will be stopped here. This side it will not grow because it will be capped here. Capping is done here. Okay. But this side it will grow how many times? N times. Now you can see that 1,4 linkage, glycosidic bond linkage, 1,4 linkage makes it linear. It makes it linear, 1,4 linkage. Again here 1,4 linkage, 1,4 linkage, again makes it linear. But that 1,6 linkage is responsible for here branching. So branching has happened through 1,6 linkage here. I hope you have understood, my dear friends. Let me mention here, it's a branched polymer made up of alpha D glucose molecules. So this is also made up of alpha D glucose molecules. And in this case we have two types of chains in amylopectin. First of all, we need a linear chain, so that after the formation of linear chain you can do the branching. If you don't have a linear chain, then branching is not possible at all. And linear chain is formed through 1,4 glycosidic bonds. 1,4 glycosidic bonds form a linear chain. 1,4 glycosidic bonds will form a linear chain. Then branching is only possible through 1,6 glycosidic bonds. Look here, between first carbon and sixth carbon there is a glycosidic bond, COC bond, and that is responsible for branching. This part will be linear. This part is also linear, but here we have a branching. So overall it becomes amylopectin. I hope you have understood this particular factor. So let us start about the cellulose molecule. Let's talk about the cellulose. This cellulose is also a polysaccharide with us. The first point is that it occurs exclusively in plants and is the most abundant organic substance in plant kingdom. The most abundant substance means present in large quantity. So in plant kingdom, this particular substance, organic substance, is present in abundance, in large quantity. I hope you have understood, my dear friends. It is a predominant constituent of cell wall of plant cells. Okay, the plant cells do have cell wall, and that cell wall has the cellulose in it. So it means the most important constituent of the cell wall of plant cells is cellulose molecule, which is a polysaccharide. And finally, it is a straight chain polymer. So we have cellulose and it's a straight chain polymer. Why? Because there is, first of all, we have a beta D glucose in it. That's not the reason actually. The reason is this. It has 1,4 glycosidic bonds. 1,4 glycosidic bond means the chain has to be linear only. Correct? If there is 1,6 bonding, that is branching. 1,6 glycosidic bond means branch will be there. But it has 1,4 glycosidic bonds, which means it's linear, it's straight chain. But in case of amylose, you have linear chain with alpha 1,4 glycosidic bonds. In amylopectin, you have a branched chain. It has two things. Okay, one is alpha 1,4 glycosidic bond, and branching is happening through alpha 1,6 glycosidic bond. But in this particular case, in cellulose, you have beta D sugar, and here the bond is basically beta 1,4 glycosidic bonds, and it's also linear. 1,4 glycosidic bonds are linear. But only difference is that here we have beta sugar, beta D-glucose. But in case of starch, we have alpha D-glucose. That's the difference. So let me draw this structure. I hope you have written this particular thing. So let me draw the structure of cellulose molecule. Have a look. I need beta D-glucose. Correct. Beta form means OH will be up. At first carbon, OH will be up. Remember that as a beta form. First carbon, OH will be up. Okay. Now fourth carbon, we know it's H, OH. H, OH. And the rest of the carbons have H, OH. Now here H, OH, H, OH, H, and finally CH2OH. Same is the case here, H, OH, OH, H, and finally H, and we have CH2OH here. So my dear friends, H, OH, OH, H we have. Here we have H and CH2OH. These are our beta sugars. So remember, it is a linear polymer made up of beta D glucose units. Okay, and we know that glycosidic bond is which bond here? Beta 1,4 glycosidic bond is there. Glycosidic bonds. Clear? Let's have a look. This is my beta sugar, beta D glucose, and beta D glucose. Now, what will happen? This guy will give H and this guy will give OH. So what is lost here? Water is lost here. Please look here. What is lost here? Here also water is lost. So now there is a formation of glycosidic bond between, have a look, first carbon and fourth carbon. First carbon and fourth carbon. There is a formation of glycosidic bond. So let me remove this water now. So I am removing the water molecule here. So the bond formation will be like this. COC bond will be formed, and it can be represented like this. COC bond, like this. Let's remove this. What is left here? Oxygen is left here. So it can be represented between two carbon atoms like this. COC bond. And this COC bond between first carbon and fourth carbon is your beta. Why beta? Because this is made up of beta D glucose. This is beta D glucose, beta D glucose. So bond will be beta 1,4 glycosidic bond. So it was your beta D glucose, and beta D glucose. So this bond is your beta 1,4 glycosidic bond. And this guy is also your beta 1,4 glycosidic bond. Now my dear friends, I have told you last time that capping can be done here. Means this end will be blocked. You have to block this end. So how you are blocking this end? Right here oxygen and block it here. Okay. Then after that, this end will grow n times. Thousands of molecules will come and interact here. So now I can mention it like this. So it will grow n times. This side it is being blocked as far as capping, and on this particular side this molecule will react with another beta D glucose, then it will continue thousands of times. So a linear chain with thousands of glucose molecules will come into bonding together, and now this particular structure will be called as cellulose molecule. So this was your beta D glucose, this guy was your beta D glucose, this guy was your beta D glucose, and I have taken them how many times? I have taken them n times now, and now this bond linkage is your beta 1,4 glycosidic bond, this one and this one. This is beta 1,4 glycosidic bond, this is also beta 1,4 glycosidic bond, and this entire structure has become now cellulose. I hope, my dear friends, you have understood this. So, my dear friends, let's talk about the glycogen, which is also a polysaccharide. And remember, stored in animal body. And what is the location where this glycogen is stored in? The first one is liver, second in muscles, and then third one is brain. So these are the places where this glycogen is stored in animal body. Three places like liver, muscles and brain. Second point, its structure is similar to that of amylopectin. I told you amylopectin of starch, alpha 1,4 glycosidic bond and alpha 1,6 glycosidic bond. Okay, the same structure is there for glycogen also. The structure you have drawn for amylopectin, not amylose, amylopectin, the same structure is there for glycogen. I hope you have understood. You take amylopectin, okay, the amylopectin and the glycogen has same structure. But only difference is there that in glycogen branching is more. In glycogen branching is more. Branching means 1/6 linkages are more. Okay. Otherwise the structures are similar. You can write down amylopectin structure for glycogen also. It's the same thing. Another, it's a source of energy. Glycogen is a source of energy. When our body needs energy, you have to break down the glycogen molecule. It will give us glucose units. And from those glucose units, okay, we can extract the energy. And then that energy is stored in ATP molecules, which we can utilize by the hydrolysis process, correct? But the enzyme which is required to break down this glycogen molecule is glycogen phosphorylase enzyme. I hope you have understood. This was all about polysaccharides, my dear friends. Have a great time. Catch you in next class. Thank you.